begin by thanking MSC Software for organizing the webinar, and in particular for Farnaz for making this happen today. I'd also like to thank a few people that were involved in the development of this product. In particular, Alan Caserio and Doug Neal for their vision in making this happen, and also a lot of the guys that were involved in at the coalface in getting it done. Hemant Patel, David Chu, and many others that I can't remember, as well as Paresh Murthy on our team, and John Saunders, who did a lot of the work in getting this product out. This is, if you like, a follow-on webinar to a webinar we did back in February when this product was just about to be released, and that webinar was quite useful in terms of explaining to people what was about to happen. Today is going to be even more useful because I can actually show you some real problems, some real examples, and perhaps get into the practical usage part of this product in a bit more detail. The agenda that I'm going to follow is I'm going to give a very brief introduction to myself and the company that I work for, and then I'll talk in detail about the frequency domain method of working. And in particular, I'm going to compare that methodology with the time domain approach to doing similar analysis tasks. In order to address the question of the frequency domain and how to use it, I'm going to talk about something called loads conditioning, in particular Fourier transformation methods for converting time-based loads into frequency domain loads. And then I'm going to address head-on the issue of accuracy. Is this approach as accurate? Is the frequency domain approach as accurate as the time domain approach? Then I'll talk about Nastran embedded vibration fatigue, the topic of this webinar. But before I do that, I'll talk about CAE fatigue vibration, which you can think of as a standalone version of NEVF, and I'll explain the differences between the two and how they relate to each other. We'll then talk specifically about how fast it is, how much disk space it uses, in other words, performance issues. Then I'll talk about some recent technical developments that have made this possible before going into some of the live examples. I'm going to try to make sure I cover the first part fairly quickly so I can spend a bit more time on the live examples. And then depending on how much time I have left, I'll talk about some things we're doing for the future, which I think are quite exciting. So as I said, my name's Neil Bishop. I'm the CEO of a company called CAE Fatigue Limited. And I spent most of my working life thinking about the issue of doing frequency domain analysis and how it compares to time-based calculations. Inevitably, those kinds of questions fit into the framework of doing fatigue analysis with FEA codes. And then it's mostly relevant to the case where dynamic response is important or resonance is possible within the structure, but not exclusively. These methods also are perfectly applicable for static problems. So that's something I wanted to make clear. So the company itself, CAE Fatigue, was set up just a little bit more than 3 years ago. And I've had a number of questions recently asking me, am I mad setting up a company to make software to do fatigue calculations? Don't we have enough already of these kinds of tools? And actually, if you look out there, there are a lot of tools that look like they fit into this solution space. But actually, I was very frustrated by the fact that when I wanted to do calculations in the frequency domain, I couldn't do calculations in the way I knew they could be done. I'd been told when I was just a teenager at university that the frequency domain offers many enormous and great advantages for doing these kinds of analysis. And actually, I couldn't see them. I couldn't see the advantages. So the frustration that I had at that time caused me to set up this company and to develop this product. The company is called CAE Fatigue Limited, and the product that we developed is called CAE Fatigue Vibration, or CFV for short. And as I said, that was developed primarily out of frustration in terms of not being able to do what we wanted to do. Now, you might also ask, well, why work in the frequency domain rather than the time domain? And the answer to that is that the frequency domain offers a lot of advantages, and we'll talk about some of those during the webinar. But nevertheless, because of the practical limitations that have been associated with the frequency domain, a lot of things are still done in the time domain. For example, nearly all automotive companies do full body fatigue calculations in the time domain. And actually, there's no real reason for that now, except that's the way it's always been done. And I've often talked to people about this now that people are beginning to see the real advantages of working in the frequency domain. A lot of people say to me, if we had to do this again, we wouldn't start from here. And that's quite an interesting concept, that if you were to develop a fatigue and durability group from scratch, where would you focus your efforts? And I can guarantee you wouldn't focus them on doing traditional time-based fatigue calculations, because they're very computationally expensive, and they don't give you information that the frequency domain approach can give you in terms of diagnostic information and basic understandings of the structure. So that's what we're going to talk about today. Although I said the frequency domain isn't used very much in many areas, I'm really specifically referring to fatigue calculations, because the frequency domain is used extensively for analysis. And this is just a list of some of the areas where frequency domain methods would currently be used in the aerospace and space industries. And if you look at defense, ground vehicle, and offshore industries, again, you'll find large areas of the analysis procedures for these types of structures would currently be done in the frequency domain. And if we look specifically at automotive examples, these are areas where there's a mix, but certainly there are areas where more frequency domain work could definitely be done, even fatigue calculations. So that's really what I'm proposing. So what is the relationship between the time and the frequency domain? This is a key question to ask. What is the relationship between a time history of, let's talk about an input load in the form of acceleration against time. What's the relationship between a time-based version of that we see here in the top part of this chart, and an equivalent frequency domain version? Well, the equivalent frequency domain version would be something called a power spectral density, or PSD. And immediately we have our first hurdle, because most people don't have a clue what these things mean. In fact, they seem like black magic to a lot of people. The units to start with seem like black magic. Actually, they're very easy. Once you start using them, they're just as practical, just as easy to understand as time signals. It's just we haven't really thought about it very much, what they really mean. So we can transform any time signal into an equivalent frequency domain form. And if we do it correctly, it's the same thing. That means you haven't lost accuracy. You haven't thrown anything away. You can do the same things with the PSD in the lower part of this chart that you can with the time signal in the upper part of it. What happens when we move on to something a bit more complicated? What happens if we look at something where it's not one time history of load that we're dealing with, but several? Take the example of a bracket hanging off a truck trailer chassis. You'll have an X load, a Y load, and a Z load. Now, in the time domain, you'd apply those loads simultaneously, so the correlation would be dealt with automatically as part of the analysis procedure. In the frequency domain, you need the PSDs for the X load, the Y load, and the Z load, but you also need the cross PSDs. So down in this lower right-hand part of this chart, you'll see a table. Let's call it a matrix. I call this a PSD matrix. And this contains the PSDs for XYZ. It also contains the cross PSDs between channel 1 and channel 2, between channel 1 and channel 3, between channel 2 and channel 3. And actually there are two parts to each of those terms, and one part represents the real, so-called real part of the correlation, and the other term represents the imaginary part. Think about a car driving down a road. Both front wheels, it's a very big pothole in the road. Now that's the real part of the correlation. You need to deal with that in your analysis output. On the other hand, if the front right wheel hits a pothole, and then 1 second later, the rear right wheel hits a pothole, the same pothole, that's the imaginary part of the correlation. And both parts are needed, and we have to take care of this when doing our analysis. And that's really where a lot of mistakes have been made over the last 10, 20 years, and where nowadays we know we can do this correctly. And we can not only do it correctly, but we can manage it in a way which makes it easier for the user. I'm going to talk about that in more detail. So yes, we can make these equal, and we can do that for real-world loadings. So if we think about a typical duty cycle on a car or a truck, that will involve more than 3 channels, more than 3 inputs. In this case, we're seeing 12 inputs to this truck, 3 inputs at each corner position on the truck frame. And those 12 inputs represent a single event. So, for example, we might apply event 6 for 1,682 seconds. We need to have all the events that apply to this vehicle in order to create the complete duty cycle. The same thing is true in the frequency domain. So we have to convert each event, each set of 12 time histories into an equivalent PSD matrix. And that's hard to handle. So one of the things that we now know is it's not really realistic to expect a user to handle all those individual terms. So one of the things we do in our software now is we manage this. We manage the housekeeping of the various subcases inside that matrix, and specifically which channel is applied to which subcase in the structure. That's all handled automatically. The user doesn't have to deal with that. And it's done per event. So the original time-based duty cycle had 10 events. So the PSD matrix form of duty cycle also has to have 10 events. And each of those events has to have the duration. That's very important. So handling the durations is a key part of the frequency domain duty cycle as well as the time-based duty cycle. So we can make those equivalent. That means we can take any number of events in time-based form and transform them into a frequency domain form in the form of a PSD matrix. Let's go on one step further. What about if we want to take one of those PSDs and make an equivalent sine sweep? Not a time history that it originally came from, but something quite different, a sine sweep. Well, we now know that we can make these equivalent too. And that's something I'll talk about a bit at the end in the future work section of the webinar. Okay. So we need an elegant and efficient way to handle the analysis procedure. And then once we've finished, and assuming we did it correctly, we get responses on our structure. Let's talk about stress, because we're talking about fatigue in this webinar. So we get a stress response, and then we need to do something with it. And this is one of the key advances that's taken place over the last few years, in that nowadays we further reduce that PSD down into the form of so-called spectral moments. In particular, we calculate 4 of them, M0, M1, M2, M4. Those 4 moments then completely represent the response that we had in the form of a PSD. Now, why is that important? Because that data reduction gives us so much performance improvement, we can start to do really nice things in our analysis. The analysis can become almost real time. So instead of taking hours or days to do a calculation, we take minutes or even seconds or even just 1 or 2 seconds to do a calculation on a very complicated structure. So this is a really key part of the advances that we've been doing over the last few years. Now that all fits into the analysis flow where we have input loads, these PSDs we've been talking about that were originally perhaps time histories, but some people start directly with PSDs. Then we need something about the structural system in the form of transfer functions. But that's where our solvers come in. We're talking about Nastran today. That's where Nastran comes in. It gives us those system properties. And then we combine these two in a simple multiplication to get the response PSD, or response PSDs, because there'll be more than one output point. And those response PSDs are then reduced down into the moments. So you see that analysis process and the moment calculation now become very simple computational tasks. The big advantage then can be seen. So let me just emphasize again, with that system flow, it's linear. So it's a linear multiplication of the input loads times the system properties to get the response. We've decoupled the loads from the system. Now, if we look at a typical large vehicle analysis that we might in the past have done the calculation in the time domain. So here we've got a case where we've got multiple events in the form of so-called RPC files. So RPC file for event 1 all the way up to RPC file for event n. Let's give an example to that. That might be 100 events typically there. Now, traditional methods would apply those time histories into a solver run. Let's talk about Nastran solution 103 to get the modes, solution 112 to generate the so-called modal participation factors. Those would be combined at the end with the stress fields from the modal run to generate the time histories of stress, which would be used for the fatigue calculation. You need to do one of these solution 112s for every input load, because the input loads are necessary in order to do the dynamic calculation in the solution 112 run. So for 100 events, you need 100 Nastran runs. In the frequency domain, you still do the solution 103, the modal calculation, but now you do a single frequency domain, so-called steady state or harmonic analysis for the whole system. And you bypass that result with your events. You do the conversion to the frequency domain, and they then come in at the end. You only do a single transfer function run. This is at the heart of why the frequency domain gives such a big advantage in terms of doing calculations on very large multi-event systems. So frequency domain is really a big step forward for this kind of analysis. So to put all that together, we do the calculation, we apply our PSD matrix of loads, we use Nastran to generate our system properties. That eventually gives us the stress responses. We then calculate moments from those stress responses, and those moments are used to calculate anything else that we want, including fatigue damage, but not only fatigue damage. You can calculate peak responses, you can calculate ranges, you can calculate many, many things. All the same things that you can calculate in the time domain can be calculated from those moments. So this is really the basis of why the frequency domain gives us so many advantages. And there are things other things we can do once we're in the frequency domain. We can do things like cascade the loads through the system. Now, some people ask me, isn't this multi-body dynamics? Well, it's related. Multi-body dynamics is used to cascade loads in the time domain through a nonlinear geometrical system. For example, the wheel system of a vehicle. So you take road load data, create body loads on your vehicle. This is different. This is a frequency domain transfer of the loads from the body loads up to some other position within the structure. So take, for example, you've analyzed a complete vehicle, and you then want to know what the loads are at the battery location in the engine compartment. This can be done. If you want to know the loads for one of the electrical units somewhere else higher up in the vehicle, inside the vehicle even, that can be done with this. So you can do one global analysis and then create cascaded loads at the local component level, and then do sub-analyses from that point on. You can also do correlation with tests. There are many, many advantages of this kind of process once it's implemented, and this can be done simultaneously with stress and fatigue calculations. So a lot of things that we can do better in the frequency domain. So a quick comment about the loads conditioning process, the Fourier transformation process. This has perhaps been part of the problem with doing fatigue calculation in the frequency domain recently. People have very often done analyses, got inconsistent results, and then blamed the frequency domain method in general. Actually, my experience is it's nearly always down to the loads conditioning, i.e. the Fourier transformation process from time history into frequency domain form. We've put a lot of effort into improving this process, making it more user-friendly, and making it less likely that the user will make an error. So if we think about the case I talked about earlier with a multi-event, multi-channel system, and we want to convert all of this into PSD matrix form in one go, we have a toolkit for this called Time to PSD. And what that does is it creates the PSD matrix for each event, retains the duty cycle durations, all the things we need. It does it automatically for the user. It then gives you other capabilities. So, for example, we have the ability to generate the matrix and then say what would happen if the correlation terms were switched off. So we can empty the correlation part of the matrix and proceed with the analysis to see what the effect was. Now, why would you do that? Well, sometimes people want to know how important the correlation is. Maybe they don't have it, and they want to know how bad their result will be if they proceed without using the correlation. So this is the reason that we implemented this. So a quick live demo of this time to PSD tool. So we have a capability which allows us, without going into the detail of this, which allows us to read in multiple events in the form of RPC files. These are the time-based loading files. Convert those into the frequency domain, and you see it's done in 2 seconds for those 14 events. And then I'm graphically now showing the PSDs and the transformed data files. Now, the key thing here is the conditioning involves several things. One is we have to make sure that the non-stationarity of the data in terms of its frequency content is taken care of, as well as the non-stationarity in terms of its intensity. So there are 2 parts to that. First of all, we have to apply what we call deletes to make the non-stationary frequency content stationary. So we split the data up into smaller events. And then we further process that to remove parts which don't belong because they don't have sufficient intensity. We've also implemented an automation which calculates the window length automatically. That's the Fourier transform window length that is such a hard thing for a user to calculate. So we've already got what we call semi-automated conditioning, and we're working hard to fully automate this, and we're confident over the next few weeks and months that we'll have that full automation in place. We think this is a really big step forward in the overall field. So I said I'd talk about the issue of accuracy and deal with it head on. Well, there was a paper published in 2016, and the authors involved people from Ford and other companies, and we looked directly at the comparison between a time-based calculation on a component like the truck cab or a subframe or a bracket, all sorts of different components. We did a traditional time-based calculation in exactly the same way that it would be done if you were doing it in-house today. And then we repeated the process with the CA fatigue vibration software. So we did these 2 things blind, and we then compared the results. And this was done in 2016, just a little bit more than a year ago. And the results were, in fact, I would say shocking. The level of accuracy was so good that people just didn't believe it. We've had a lot of people repeating this since then because they didn't believe that you would get the same kinds of results. Now, by the same kinds of results, we typically talk about anything less than a factor 2 difference in damage. We talk about that being the same result, because for a difference in factor 2 on damage, you only need a 6 or 7% change in stress. So we're typically looking for a level of accuracy within that factor 2. And furthermore, when we see a difference, it's not possible to simply say, the frequency domain had an error, because sometimes it's the time-based result that's wrong. In particular, we looked at 1 or 2 of these differences here, and when we looked into it, we found that the problem was caused by the fact that the frequency domain was incapable of going to sufficiently high frequency to do the assessment. Now, there's an interesting observation about time and frequency domain calculations when you start from a time history. The frequency domain is accurate to up to half the sample rate. So if your sample rate is, let's say, 1,000 hertz, the frequency domain is accurate to 500. On the other hand, the time-based analysis is only accurate to between 10 and 20 times that highest frequency. So again, going back to the 1,000 hertz sample rate, it's only really accurate to 50 or 100 hertz. So you get a much higher level of accuracy at high frequencies working in the frequency domain. That's a really important point that is overlooked a lot of the times. So this, I think, was a breakthrough paper because it really demonstrated that the frequency domain, if applied correctly, could give the same level of accuracy as the time domain. So Nastran embedded vibration fatigue, that's what I'm going to talk about today, is, well, and really I'm talking about CA fatigue vibration. I'm talking about the technology sitting inside that. We call it a second generation frequency-based solver because we've removed a lot of the practical limitations that existed with previous attempts at a similar capability. So some of the important points about what we do now, we do both random response and fatigue in the same runs. That's quite important. We focused very much on user ease of use. So we think it's very simple to implement. It's much more robust than previous offerings. It's suitable for very large models, much more flexible in terms of the way you can mix random and deterministic loads. And very important, it's suitable for, and not just suitable, but totally applicable for multiple simultaneous inputs of up to, let's say, 100 channels or more. And that could be done for both modal, solution 111, and direct. And I should also say it's also totally okay to do it for static analysis problems. So just because you're working with a static model doesn't mean that this process won't work. We've also done a lot of work with optimization that I'm not going to talk about today, and we've done a lot of new work with the load conditioning time to PSD expert system that I talked about. So Nastran embedded vibration fatigue, I'm going to talk specifically now about that. I'll start by telling you what it isn't. It isn't MSC fatigue. MSC fatigue is a Patran-based fatigue tool set that sits inside the Patran GUI. It's also not MSC Nastran embedded fatigue, which is a time-based embedded solver that is already inside the MSC Nastran product. Nastran embedded vibration fatigue is an advanced frequency domain random response and fatigue solver. So the difference is between NEF and NEVF. NEVF is a frequency domain solver. So that's really what I'm focused on today. So let's go into a little bit of detail then. So at a high level, what's the difference between NEVF and CA fatigue vibration? It's very simple. It's very simple, but very important. CA fatigue requires the stress solver to have done its job before it starts. So we assume that Nastran's run, an OP2 file's been written, and then that becomes an input to the CA fatigue vibration process. Works very well, but it's limited by the fact that this OP2 file can become very big, and also Nastran is somewhat limited because because it means Nastran has to do a lot of stress recovery here, which isn't necessarily needed. So in simple terms, Nastran embedded vibration fatigue is simply taking the CA fatigue algorithm, the technology, and putting it in a loop with the stress recovery inside Nastran. So Nastran proceeds to do stress recovery, and for each frequency response function it recovers stresses, it then works with the CA fatigue vibration solver to do its job in terms of calculating response and the moment reduction that I talked about earlier. It then throws away anything it was using and moves on to the next frequency. So there is no longer any need to do stress recovery. And that gives tremendous benefits, both in terms of speed and disk usage. And I'll talk about that in a couple of slides. So the next couple of slides just show the same thing. The standalone product requires Nastran to do all of its calculations, put everything into one file, and then the CA fatigue code interrogates the OP2. When it's embedded, that's not necessary. The CA fatigue code can be passed those stresses in a very elegant, efficient way, one by one, and then never has to keep them stored. Everything can be done in memory, even for really large models. So again, just summarizing then, why Nastran embedded vibration fatigue? Because it really is a breakthrough in dynamic analysis, making the frequency domain practical for both random response and fatigue. I'll talk about performance shortly, but for the die-hard Nastran folks that are on the line, I want to show some Nastran cards. I'm not, well, I am, but I'm not going to do it for very long. I'm going to whiz through these really quickly. But at the heart of this process is a are an additional set of Nastran entries. So for those of you that are familiar with Nastran, you'll be familiar with the way Nastran works in a deck format. As I said, I'm not going to focus on this at all. I'm simply going to show very quickly examples of how this is done. So we have cards to request output. We have cards to define material properties, cards to define the various parameters for doing the calculation, how to define loads, how to sequence those loads, how to set up complete jobs with multi-events, multiple loads, and we're going to look at this example as a real live example. How to apply static offsets. This is all done inside the Nastran deck. How to apply sweeps, that's also done inside the deck. So, okay, that's fine, and I went through that quickly because I'm aware that it's not particularly attractive to be showing Nastran deck entries in a webinar. But this raises an issue. How do we control this process? How do we process a job through Nastran and make it user-friendly? So you have a number of options for this. So I want to just explain how this can be done. Option number one is to use Patran to set up your job, run Nastran, and then you can plot the results using Nastran. And those pre- and post-processing capabilities are fully functional. So that's option number one. Option number two is to use our GUI app wizard to set up the job. And what's nice about that, we have some template files I'm going to show you that allow job setup to be done fairly easily. Then convert that directly into Nastran format with our wizard, and then run Nastran and plot the results using our wizard. So that's a very straightforward option, number two. Option number three is to do the same thing, but within our GUI app, we can also write out a Hyperview file, and then you can use Hyperview if you want, if you're already required to do so. So these are the options that we have, and I'm going to focus today on the template file option because I think it adds a lot of value to the possibility. So before I do that, let me just address performance. Here's a quote, a nice quote I got from one of our users. I'm going to talk first of all about CA fatigue vibration, CFV, and how that compares with other procedures that have been out there for the last 10 or 20 years. And I got a comment from a user. It said, this CFV job ran in 4 minutes. Before it took 6 hours. That's 100 times improvement. And that's very typical of the performance improvement we're getting with this technology. Now, that's just the improvement standalone. Now we put that inside Nastran, and we then have the chance to improve the performance of the Nastran part of this calculation. So here on this chart are three things. First of all, I've got a line here saying limit of some first generation solvers. Very often really big models, and I don't even think that 10 gigabytes is a big model, but models above that will cause problems with some toolkits. So there is definitely a file size issue with many of the existing solvers that are there today. And one of the first things that we encountered with the CA fatigue vibration code was that it has a linear performance against file size. So we've handled models up to 2,000, actually that's wrong, 3,000 gigabytes a customer handled the other day. So multi-terabyte files are perfectly feasible. There's no issue with that. Now what Nastran embedded vibration fatigue does, it reduces the run times typically by a further factor of 5 there. Okay, so that's a really big improvement that you get. So you're getting improvement in run times. We're also going to get improvements in disk usage. So a typical disk usage, this is showing disk usage on the vertical axis for what we used to get when running Nastran on its own, having to write out an OP2 file and using CA fatigue on top of that, and then running the two combined. That's the NEVF one, the blue one. You see, that's the factor 5 improvement we get on disk usage as well. And just as a reference point there, there's a real-world car model of 2 million elements, and that's where it came in when we analyzed it. It was a nice reference point. We get similar performance improvements on runtimes. That's the factor 5, roughly factor 5 improvement I talked about between CA fatigue and Nastran running one after the other, and running combined. And that's the car model point that we got, just as again as a reference point. So these are really nice performance statistics that that we're very happy about. So I'm going to talk briefly about the new developments, really briefly, because I want to move on to the examples. There were a lot of things that were holding back this technology. We talked about model sizes. We talked about correlation of loads and mixed loads, the loads conversion. I didn't talk about material properties, but another thing that used to hold back a lot of the other codes was that the frequency domain approach required stress-based properties, and they wanted to use strain-based properties. And we support that, along with Neuber corrections. And the bottom item there is the issue of accuracy, which we've already talked about. So these are the things we've addressed. We've done it with faster algorithms, which can handle larger models, and these different techniques that we've implemented, including things like the ability to handle seam welds, and we're looking at spot welds right now. The fact that we can analyze shells and solids at the same time, we can do sine sweeps and mixed loads. And we have, in the standalone code, some really advanced random response capabilities as well, which one of the things that we can do with that is collision detection. So really advanced methods that we've been developing. I have a slide on each of those, or on many of them, and I'm not actually going to dwell on these. These will be supplied in. If anyone wants a copy of these slides, they can be supplied. So I will leave these slides in the deck, and they will be there if anyone wants to look at them. But there are a couple of slides on the strain-based material properties and the Neuber correction that we do, and how we do it. There's a slide on how we average stresses for both center and corner results, how we mix loads, how the sine sweep is implemented. I do have an example on that, so I can show that shortly. So that allows me to move on to the examples. I'm going to begin by talking about the CA Fatigue software and how we interface that to provide a wizard. And that wizard is also something that we think can be valuable for Nastran embedded vibration fatigue users. So this is the interface of CA Fatigue vibration, and this is the wizard when I click on that button there. And within that wizard, we have a series of tabs. We also have access to the software and also access to a lot of training material. So if you're wanting to get up to speed with some of the background technology, this wizard provides direct access to nearly 100 hours of training material. The rest of these tabs are job setup tabs. So you have a choice. You can set up via a wizard, which is a kind of simplified GUI on the right, or you can set up your job in a Nastran format over here. Both are perfectly acceptable, and you can do one or the other, or in fact a mixture of both. So the wizard is really an either-or option for the user in terms of job setup. So this is how we set things up. We then have options for post-processing. I'm going to talk about that when I run one of the other live models. Okay. So I talked about these processing options, and I'm going to focus on this one, where we start from a template file, we go through the wizard, we'll convert that into Nastran format, run Nastran, and then read the results back into the wizard. So that's what I'm going to focus on for the next 3 or 4 minutes. And I'm going to do it with a live example. So it's a truck cab example, and I'm starting off from our wizard, and I'm going to go to the template option on the upper right-hand side, and I'm going to read one of our templates. Now, you'll see I'm picking Nastran. There's a limitation here at the moment. It says 3 events, but I'm actually reading in a 12 event model. But there it is. I'm reading in a template for Nastran 12 events with the mean and PSD inputs. It's asking me to save this because I mustn't overwrite the template. So I'm going to call this TPL56. And that's now my CA Fatigue job. Okay. Now, I'm going to, this has everything that we need to run the job, but it's in CA Fatigue format. And now the difference between CA Fatigue format and Nastran embedded format is trivial. It's a very small change. But what we can do, and we're going to convert into Nastran format shortly, but before that, we're going to go and make any changes to this template that we need to make. So this is where we can go into the wizard and go through all of our settings, check if they're what we want, and where they're not what we want, we can go ahead and make changes to them. Because, of course, the template will point at a reference OP2, and you're going to use, or reference model, and you're going to use a different model. It'll point at different loads. It'll point at different materials. So in here in the wizard, you can go ahead and point at the loads that you want to use, the materials you want to use, and so on, and get the file exactly as you want it. And then what you'll do is press the convert button. Now, for those of you that are more observant, you'll see there isn't a convert button here right now because it isn't in the wizard yet, but it's being put there as we speak. And what that convert button does is it writes out the deck on the right. The deck on the right is the same data, but in Nastran format. So if I just take a look at one part of it, look, for example, at the, well, the PALM's a good one to look at. The VFTG PALM on the left is CFB format. The VFTG PALM on the right is Nastran format. And you see they're the same, almost the same. And they're mixed up a little bit, but the entries are the same. So we have this translation process, which allows us to create the Nastran format. Now, you're going to have to add into this, because it's got to be a file capable of running a Nastran job. You're going to have to read in the Nastran part of this, which is the model, the subcases, the case control. So you need to have all of that available, and you need to read that in. So you'll see various includes here, where those are read in. You'll see the loads there. So these are essentially identical fatigue setups, with the Nastran form on the right having, in addition, the includes to provide the model. So you see include cap static. That's where in fact, that's where the model is read in, and that's got a typo there because it's not OP2, it's PDF. So now we can go ahead and run that with Nastran. Okay, and if I run that, I've already run it. It takes about 5 minutes. I then get a set of results, and those results can be read back into the wizard or the GUI. So I need to load the model cap2.pdf, and then I can graphically plot the Nastran embedded vibration fatigue results in the CA fatigue GUI app. And so that's what I'm doing here. So I have fringe plots for stress, and I have fringe plots for many other result quantities on the left there. I'm not going to go through them all in detail, but one of the important ones is obviously damage. So that's a very quick introduction to how the wizard can be used to create a Nastran input file, and then can be used to plot results. We also have many other examples in Nastran format. One of them is a sine sweep example on this bracket. So again, I have an example showing how we set this up, and I'm going to go through this fairly quickly because we're running out of time. Again, setting it up inside the CA fatigue GUI, we have these sine sweep options. We would do the transformation back into, so these sine SWs are the way we specify the sweeps. We're applying 1G from 1 Hertz to 20 Hertz. You see this is the wizard option for that. And once completed, I can read those back into the GUI app and plot the results. For example, I can plot the results as a function of sweep position. So here are the Nastran embedded vibration results for the sweep, showing whatever quantity I want. This is showing damage, but I can also show stress. If I change the result quantity there to RMS stress, it'll show me stress as a function of frequency position for the sine input. So that's another one. And I'm going to finish off with the examples, looking at a really large truck trailer frame, which is 87 events. I think it's 80 inputs. It's run inside Nastran, and I'm going to read those results back into the GUI app and plot them to show you the kind of powerful results that we can get out of this kind of analysis with Nastran embedded vibration fatigue. So you can see this is a very large model with 87 separate events. I think it's something like 80 channels in each event. The whole thing's set up inside Nastran. It's been run. I'm going to load the model so I can plot the results onto the model. So I'm loading the mesh data there. Then I'm going to go and initially plot the fringe plot. So I'm going to go to the 4th icon, show the fringe plot results. And by the way, this model takes around 8 minutes to run. It's a 1 million element model. These things are running really fast. So this is the model, and let me enlarge this a little bit so we can show it in a bit more detail. Just drag this screen out, and if I go up to my results options, I've got all the same results options. Let's start off again with stress. So this is the stress at each output point. Now, I did use a slight filtering option. We have something called top RMS. You see up there, it's 98%. So I've removed the bottom 2% stress results in this model just to make the results easier to plot. It does also give a slight performance improvement as well. So RMS stress is one result quantity. And I can also plot that as a function of events. And we have the 87 events here. So if I go through, I can go through and plot each one, and I can see which one does the most stresses, the highest stresses, or the most damage. But that's cumbersome to go through them one by one. But actually, we have a better tool for that. So if I want to quickly look at that result as a function of the applied events, so this is damage for event 4, for example. Okay, rather than going through each event one by one on the fringe plot, let me go to the event plotter. This is going to give me a really quick view of the result quantity, whichever one I want. This is stress, as a function of event. And I'm seeing that the 61st event is the highest stress, and not surprising, it's the biggest damage. And I also see, so if I go to 61 in the fringe plot now, I'll see that damage. Okay, so the event plotter is a very useful way to see the result quantity as a function of event position. We also have another tool for showing the PSD response for a particular event. So if I go to event 61, I can now see what PSD caused that result. And I can do that for any event I want. And I can show with that the result quantity that was created. So this is very powerful results plotting of these capabilities. So we have a bunch of papers that cover a lot of these topics. If anyone wants these, please just drop me an email or ask Farnaz, and we'll send these to you. And we have other material if you want it. I do have a lot of material on future work I wanted to talk about, but time is running out, so this is going to have to be rather quick. The advanced loads conditioning, we talked about that earlier. I won't talk about it anymore. Perhaps the one topic I will talk about is surrogate loads. Surrogate loads is our way of creating equivalent simplified loads that do the same damage as more complex multi-input, multi-event loads. You may have heard of something similar. Fatigue damage spectra are a way of calculating equivalent damage inputs, but the fatigue damage approach applies to hypothetical systems. So the difference between what we're doing now and what fatigue damage spectra try to do is that we do it for real systems. So we're able to calculate equivalent loads that do similar damages to complex multi-input, multi-channel loads at various monitoring points on the structure, and we can do that in an optimization process. It's a very cool process that we have for doing that. We can do that for quite complex systems, and there are papers published on that. 2 of the papers that I referred to earlier will cover that. An extension of that is something called analytical loads development. So if you take those simplified loads and you then try to parameterize them, make the loads a function of something that you know. For example, in the offshore industry, wave height and wave period is something that can be measured. Those 2 parameters are used to create analytical loads very successfully in the offshore industry. I'd like to investigate similar things in other industries, especially the automotive industry. And an extension of that is then the concept of modularized design. So if your design process has more than one option, then enveloping is a way that can be is a process that can be used to understand the implications of that modularized design process. We have a paper on seam weld fatigue. You can read it. I'll share it if anyone wants it. We're very interested in acoustic analysis using spatial temporal correlation. We think our approach is ideally suited to setting up and running these jobs with patch loadings on FE models. So if anyone's interested in that, please do contact us. We'd love to work with you on developing that capability. Something else we're very interested in, we have colleagues working on something we call fatigue map, which is a concept of, if you like, condition monitoring, but condition monitoring for fatigue real time. And again, we have some papers on this, which we'd be happy to share. And if anyone's interested, please contact us. This is a roadmap of where we are with our software, and that's where I'm going to finish and leave at least some time for questions. I've also put some next steps of what people might want to do following this webinar. If they want to try Nastran embedded vibration fatigue, then you know that they should download it. I would specifically recommend MSC fatigue users try that for their frequency domain work. If you're an MSC Patran random user, you might want to try it, or an MSC Nastran random user. I mentioned the acoustic patches, but essentially, if you want to do some benchmarks and do some trials with this stuff, we're here to help. With that, I'm going to pass it back to Farnaz. I'm just a few minutes later than I wanted to be, but I think we still have some time for questions.
Thank you so much for the very informative webinar, Neil. We do have time for some questions, so please type in your questions in the Q&A panel. Okay, I see that we got one. What materials are available, and can we make user-defined materials?
Yes to the second one. User-defined materials are very straightforward. The answer on the other materials question is we have standardized definitions of our materials. So any existing materials that you're using will directly feed into this process. We use processes for defining materials, which you'll thoroughly recognize. They're the same processes that are used by more or less everyone else. So anything that exists out there today can easily be fed in, is the answer on the materials side.
Great, thank you. How do you combat your RMS stress in damage? Whereas is the time number of cycle in the PSD definition?
Right, so the first thing is we don't use RMS directly, only indirectly. The RMS is a function of what we call M0, which gives an idea of the intensity. So that's one part of the ingredients that are used to do the calculation for damage. The other part is a rainflow cycle count, which we do with the other moments. And then that rainflow cycle count is used with the number of peaks per second, which we calculate using M4, M2, and M0. So all the various moments are used to calculate certain parameters, and those parameters are then used to do an absolutely standard fatigue calculation. So we calculate number of cycles per second, we calculate the rainflow count, we combine that with the number of seconds in the duty cycle, and that's then used to do a fatigue calculation. And if you follow the process through, it's almost identical to the time-based process. The only difference really is how the rainflow count is developed. In the frequency domain, it's developed typically using something called Dirlik, but there are other options. And in the time domain, you would directly count it from the time history.